the cancer bone and how much portion we need to cut. Just you can supply these models to the say surgeon and let them to practice on that. So not on the patient during the surgery. So they can have that opportunity. And then weight optimization, again, you can take the advantage of topology optimized structures. That is well, the weight optimization or the topology optimization. So can be done. Why? Because again, in order to minimize the weight and encouraging the cell growth, so then you can adopt a lattice structure sort of design. So initially, this is in a modeling software where this implant initially we suggested to the surgeon, and then um, further it has been say um, this is what where this got designed and then say printed in the lattice based structure. And we have come out with different designs, but these designs are not encouraging its a solid um, rather than a sort of lattice structure. Lightweighting, not only lightweighting, so it also promotes the osseointegration of your um, bone with the implantation, and even for the tissue growth, it also encourages the tissue growth. So, like we have several advantages once you come to the lattice based designs rather than a sort of a plain designs. So, and uh, you may wonder why still that models are not gone inside the patient mouth. Then we came to know that there will be several procedural things which we need to, just like that we cannot implant inside the patient mouth. We need to take the sort of clearances from the ethical clearance team and the other formalities. Though we'll take the consent from the uh, patient, but still we need to follow several formalities or several uh, regulations or the sort of things. But at least what this is our first attempt, but we could not succeed it. But what we have done, at least we have supplied the models for them to say fix these sort of plates conventionally what they do. But at least we have supplied these models for doing that, say fixing that plates or the steel plates for getting the form of the correct form of the patient. Say, and then they normally what they do, they will take the fibula bone, and so they say fixed here. It is a native bone or the geometry or the form, or it never formed. It never say the bone grafting. Why I'm saying is they again they came back to us like saying that there are complications. The surgery is not a successful surgery. Can it be opened further and can it be done? Why? Because we have already designed and fabricated the implants also. So like that way where you have the conventional traditional methods, surgical methods are not working out. So definitely 3D printing technology is helpful for solving such sort of surgeries where the conventional methods are not worked out. And the next case, the fifth case, is which we have succeeded in this case. This is a TMJ ankylosis surgery. So that is so temporomandibular joint ankylosis. Um, you see, this patient is 21-year-old female patient. She had a birth issue, birth problem. So, you have the lower jaw and you have the upper jaw and you have the joint here. So that joint is called TMJ, that is temporomandibular joint. So that joint, you have two joints, right? So this is a one on the left and other on the right. So she had a birth problem. So by birth she had the fusion of that joint from one side. That is the issue. So because of that fusion of the joint, she had say the the occlusion is not happened properly, and even the the sort of mismatching and not opening the mouth, normal opening mouth, even she could not even able to open even a 1 centimeter. So normal opening is 4 centimeter. So then she had a problem right from the birth. She had a problem in that way. So then we thought like for the past 20 21 years she has been like that. So then if we take up this case and then if it succeeded, and definitely that is going to be the new societal life for her, like where that's what we took this case. And this is the where I'm talking about. If you see this joint from the ramus portion, from the mandibular to the zygomatic portion onto the maxilla side, so it should have um, normal articulation, means it should have form, easy opening. That is responsible, the easy opening of the mouth is responsible, this joint, but this joint got fused. So that is the major uh, problem, and that it should be getting operated, and which we should say reconstruct this joint basically. So if you ask an oral maxillofacial surgeon how complex a TMJ reconstructive surgery, so that is a quite challenging, which we need to retain this joint. So but luckily she had other side joint, and then we can take the help of that geometry, assuming the symmetricity from that side to this side, we can copy, and then we can able to do that part. So it goes two level surgery. The first surgery is to again the distraction osteogenesis, so that the same surgical procedure we discussed in the previous cases. So we need to leave the gap here, and slowly stretching forward this um, the the mandible, which you can see 1 mm, 2 mm, 3 mm, 4 mm, 5 mm, like that. Slowly, it's getting stretched forward. So initially, you see the closing of the mouth is not happening properly. Then slowly, if you stretch forward this to up to 19 mm, 20 mm, so where we can find the the sort of alignment here. So then this is what which we need to do this, and that is during the surgery, during the transformation of that surgery. So where you can very well plan that how much we need to stretch forward, like the how many revolutions, so that it needed in the real time to advance this bone, right? uh, and this is during the surgery where we can see say fixing that distractor and stretching forward that bone with the help of this distractor. So slowly during the transformation where 2 mm, 3 mm, the same thing which we have planned before the operation, the same thing which we are going to say replicate during the surgery. So this is during the transformation. So this is the one, um, say the first level of the surgery has been say successful, which we can see before the surgery, the after the surgery. Now she got say right alignment of these teeth, and but the major part left out here is like it is got fused. So then this fusion of the joint, so the zygomatic arch and the condyle and the fossa, where it will create a disc or a joint here. So where it will go and insert. So this, and you have a complex nerve system here, very close to the joint. uh, that's what where it will become very complex in nature, and then you are straightforward, you are going to say um, reconstruct the joint here by dismantling that joint, and then you are going to replace with some implant here. So that's the thing where we need to do right now. So then you start with taking um, the images, reconstructed images, and this is what I'm talking about, where we need to uh, dislocate, discard this um, joint, and where you can take the help of other side and trying to say attain that thing here. So that's what we need to do. And you may get doubt why these images are blurred. Why? Because this we took during that distractor escaped, na? That is some of the scatters just we went. Anyway, so um, th- this is what where the condyle geometry dimensions form everything is copied from the survived side to the defect side, and this is what the condyle design. And initially we printed onto by using a desktop based 3D printer to know the form. Basically it's a prototype to checking it whether the fitment everything is okay or not. And even the fusa component, that is where your condyle will go and sit here. So this fusa again, we took the advantage of the survived dimensions copied to the defect side. So, and this is the design, and this is the model that has been printed through 3D printing machine. Yeah, this is what like it goes. Like say you have dismantled this, and that is from the maxilla side, where zygomatic plus fossa. This is what it will be on the upper jaw side, and lower jaw side your condyle, where you have designed and fabricated this. And this is the joint, and this is then assembly, the lower jaw upper jaw with this design joint. So this is what it goes. So then once we checked the fitment of the implant versus um, the bone, the model, the biomodel of the patient, which it has been mm, got from the scan, and it is fabricated, design fabricated independently, and then checked for the fitment. Yeah, and this finally it goes like this. So this is the diagrammatic side, which it has been printed, and metal 3D printer titanium 64 is the material used. And in order to minimize the metal to metal contact, say then we have come out with a polymer which is of biocompatible, which is again 3D printed. And of course, wherever you have the load bearing, but you cannot get a mirror finish from the machine. So you may get this sort of finish, but that doesn't matter the finish over there. But it may matters here where it's load and your biting force, it will come here, and where you have mirror finished here. So, and then this is what it's going to fix during the surgery, right? So, and then we have developed um, a template or a guide to assist for the surgeon for fixing during the fixation of that implant. So this is the template used for say drilling a holes onto the skull from the upper jaw side and the lower jaw side, and this is the template. And then making use of that template, and then they have done that surgery making use of the template, and then the implants. And myself and my scholar and my collaborator is Professor Anne Gibson from Deakin University, Australia. You might have read the book Additive Manufacturing, the authored by Anne Gibson. And we have a collaboration, and we fixed this appointment of the date of the surgery during his visit to India in our collaborating project. And then I was there very well evident for this surgery. Um, And this is what, like, where so for the past 21 years she has been surviving her life uh, without opening the mouth much, uh, say predominantly on the liquids, liquid diet. Um, but at the moment, why the reason is because of the fusion of that joint. At the moment that fusion got released, now she has attained 4 centimeter opening of the mouth, and then we replaced that thing to with um, the joint or the TMJ joint which I showed you. So it got fixed from the um, upper jaw, maxilla side, and from the lower jaw, that is the mandible side. The screws with the they able fix the screws during the surgery, and now she is doing good. So she has attained now normal opening, that is 4 to 5 centimeters, and normal biting, normal chewing, occlusion, everything she has attained. So after 21 years, she had um, a better societal life than the previous for the past 20 years. So in this way, this technology is also helpful for resolving any long-term pending cases or complex cases. So it is an opportunity. So for us to make use of this technology for further better societal, not only the non-living products like automobile, aerospace, even it can be further extended for the human beings to make use of this technology. So this is the last case I'm going to discuss with you. This is a basilasio integrated implant. So this implant, so this is an accident case where he met with an accident and he lost 5 teeth, and along with the teeth, and he got a bone damage. So if you have a bone support, then you can make use of the a normal existing implants so that are available in the market, maybe from Zimmer, Stryker, or Anatomics, or any other company which you can go and just buy and fix it. But unfortunately, you don't have a sufficient bone support here to fix those 5 teeth, maybe 5 screws, and then keep fixing it. But unfortunately, this guy say damaged his bone totally, and then which otherwise it is not um, possible to fix the standard sized implants. So and then we need to attain the nerve relieving option also, that is another thing. And density of the bone is not uniform, as we know that the angle of the teeth replacement, everything we need to, and more or less it is an asymmetric fracture, like where this is an accident. We don't say that like how it's getting happened. The fracture, it is an asymmetric fracture. It has went. So then, no other way. It has forced us to design an indigenous implant. The existing implants are not worked for this case. Say that's what where your additive or 3D printing is more say attractive, like for designing and fabricating patient specific or patient matched implant. So and that too, as for the fracture, based on the fracture, then we have designed this implant with which you can see the it is not a symmetric. Why? Because it should match with the nature of the fracture he went, right. And we need to check for the failure of this implant for applying the loads and things like that, and fitment of it. So for fitting the, you have the CT data of the patient, and then you have the designed implant and check for the fitment, so how it is getting fitted, and then before you go to the actual surgery. And even further, we printed initially with the model, not exactly the implant. The implant will be printed on metal titanium 64, and this is initially we printed with a polymer based printer, desktop based printer. So for the checking of the fitment of the implant versus the bone of the patient bone, and this is what and they can try practicing that fixation onto these models, and ultimately it is left with the four teeth. The four teeth has been accommodated in this way, and your implant will be there at the back. Just initially we checked, this is a denture taken from the patient, or even it could be done through our 3D printing also, like which we can check it. Even you can compare both. And anyway, so this is the thing where this implant has been printed into the powder bed system, metal powder bed system, titanium 64 is the material, and the support structure here after post processing, removing the supports, and this is the one after sterilizing, autoclaving, and then we need to follow the regulator recommendations to do that sort of post processing during the post processing step. And once you have done all that sterilization, autoclaving, and other things, and it has been fixed during the surgery. So where you can see this is an implant that is getting fixed, and finally it has been fixed here, and this has been fixed on top of it. So the crown and the teeth will be fixed, and this we have published in a rapid prototyping journal, one of the prestigious journal in this area. But if you are interested about this case study, you can go and refer this article. And this is what where I'm talking about, like where you can see this is the X-ray image, hand X-ray right after the placement in the operation theater. This is the image where you can see the placement of the implant, and on top of it where we could able to fix these four teeth without any gap and fitting it here, right? So this is the post surgery of the patient, right? And we can see several cases. Sometimes some abnormal growth of the tumors happen, or some by birth some cleft cases. These cleft cases, or some head injuries may happen, and where so then you see the possibility of integrating 3D printing technology, some emergency cases, some head injury, major loss of blood, and you may be asked to give a model within 1 hour or less than 1 hour or so. But emergency cases I'm talking about, but that may not be feasible to do all that. Maybe minimum to minimum 1 day it will be taken to print this skull and further post processing, and then so it may not happen within 1 hour, processing the data and printing it and making use in the operation theater intraoperatively. So that may not be possible, not all the cases it's not possible, especially the emergency cases. So then one can understand, or while taking up the cases, then we need to check the feasibility of these practices by using this additive manufacturing and 3D printing technology. And so far, we are discussing, like, say, the replacement of the bones, or the replacement of the joints, or the replacement of predominantly the bone replacement has been done. But whether the same thing can be extended for the organ can be replaced, or can be transplanted, or can be repaired. So then answer maybe yes. Say in that case, what could be the material? So far we are talking about some synthetic materials or the man-made materials, either titanium, or say PEEK or PMMA or hydroxyapatite, or maybe any other material, the biocompatible material. But if you are trying to print a tissue or an organ or a cell, so definitely that's going to be the natural material, or of course it may be the living cell that has been taken from the own patient. That's going to be the material. So can that material is sufficient? But may not be. Why? Because you may add some collagens, or you may add some nutritions, or you may multiply these cells. You may do cultivation, cell cultivation, and then finally you may print from the printer, and it may be, say, a cardiac region, or it may be any other region where you are looking at. So maybe your human cells, or the living cells, may be taken as a material for to be printed, or to be cultivated, or to be grown, or to be replaced, or to be, say, repaired, or so then again we need to take from an MRI or a sort of the data acquisition, and prepare some material, and then print them and implant them. So this is the thing where people are trying to do, and then some extent some people are succeeded, some people are still trying. Then in a summary, so what is an organ printing is all about? Say they extract a cell from your own body, and they will add some nutrients, proteins, and they will do a cell cultivation in the incubator, and and you may get doubt that whether it has been attained the the same properties that a native um, bone, or the native organ, or the native tissue is having, with the same mechanical properties, or rheological properties, or the biological properties, whether it has been retained or not, or whether it is mechanically stable, the cells are stable, or the organ as a total has it been stable or not. So that is quite challenging stuff, which we but how do you check that whether it has been attained those properties or not? So then you may use some sort of bioreactors to, or you check for the properties some extent, and if it is qualified, everything is say mechanically stable, rheologically, biologically, it is, say, okay, and then you try to put it back into the human body, where you have picked, or where you have generated, or replacement, or transplanting, or repairing, or whatever it is, like maybe lungs, or maybe heart, or maybe liver, maybe kidney. And then what is the state of art of this say practice of organ printing? So of course people are very well succeeded in printing simple tissues, like skin, like bladders. This has been 3D printed. So the bladders, skin, and blood vessels has already successfully transplanted and successfully implanted. But still, you have to say think to be like, if you are extending the same to the next level of complexity of the organs, like what we discussed here, is like maybe heart, or maybe liver, or any other thing where you are looking at. So definitely we need to um, take this technology to the next level. Why? Because this should be, say, the challenges which we are talking about, it should be, say, taken up, and then it should be proven, right? So then days to come, maybe years to come. Why? Because people are succeeded some extent. The first level complexity of the organs, simple organs, maybe it can be extended for the next level of next complexity levels of organs. But time may be the deciding factor. But you can find a lot of breakthroughs in this direction, like how it is getting, say, mm, further matured this technology. So the summary what we have discussed for the past 1 hour 45 minutes. We have started with medical scanning technologies, right, from the CT, MRI images, or how it is getting processed by using medical image processing softwares like Mimix, Voxem, or any other software, a 3D slicer, open source software to make the models to be ready for 3D printing or ready for to export into FEA packages or to simulation or analysis packages or further to 3D printing. And we may use these virtual models for say some extent, maybe for the initial preliminary understanding. You may use the virtual models also, but if you want to know beyond that, then which we need to make use for diagnostic purposes. So just like form form fit function application in case of engineering, just you want to see the form or you want to know the gravity of the disease, or for diagnostic purpose alone. So then you can make use of that, the purpose of diagnostic model, the first level of application, or the next level of application pre-planning of the surgical models, like which I was explained with some of our case studies, how we have used those models for planning the surgery. Some of the case studies which I discussed, initial case studies, and then how you could able to customize your implants or customize your prosthetics. So that is also we are succeeded in a couple of cases for implantation and prosthetics also. And then even it could be further extended to medical devices. That medical devices, even it can be implantable. Not all the time it is implantable. Sometimes just it is purpose of guiding or templates or the tools. So then you can very well use that for these purposes, or even it can be extended even for support devices like arm braces, knee braces for orthopedic applications. And even it could be extended for the COVID applications also, like where I didn't discuss, but the scope will be even to uh, customize the PPEs for the specific requirement needs, or see some ventilator spare parts, which you can, that's most demanded things, or oxygen concentrators and their spare parts. So very well you can do add like some nasal swabs or oral swabs for um, RT-PCR tests or rapid tests, which we can make use of this technology in more effective way. So, and then finally we have discussed the tissue engineering, or and the argon printing and bioprinting. So, and the state of art, like what is the level of applications right now going on in this direction. So I hope I have given some scope of this and our own experience making use of these models or implants, next level of applications, which we are. I hope we have covered initially a bit of initial level application like a diagnostic or planning application, and slowly we are into the customized implants and the prosthetics, and we never been into the argon printing or the bioprinting, but that's quite interesting area where we can even think about it, and you can even collaborate to work in that direction. That's going to be an exciting field. That's the thing where you can prosper this direction. The medical application of 3D printing will prosper in that direction, but there will be several challenges that we need to address in order to achieve that. Um, yeah, and before I hand over to the organizers, I would like to acknowledge my collaborating team, Professor Dr. Shekhar Reddy and the Aditya Mohan from Panniya Institute of Dental Sciences and Research Center at Hyderabad for oral maxillofacial, related cases and their support and their collaboration, and Dr. P. Mahesh from Narayana Dental College for dental applications, and some extent cranial cases, and the financial part from DST and SCRB for financial support from the wide the R&D projects, and last but not the least, my students probably might have seen the citations of some of the papers which had been published in terms of papers or in terms of patents. So I would like to acknowledge my um, UG students, PG students, and especially the PhD scholars. The two of my PhD scholars who dedicated to work on these areas, and I would like to acknowledge my PhD scholars, um, to name Manmadachari and to name Fanindra and of course Santosh. So these are the people who involved this work apart from my UG and PG scholars. So and of course these are some of the facilities we have. We have a 3D printer, metal 3D printer, and we have a couple of status seismic um, polymer based printers and desktop based printers like Ultimaker, Scans and Scan for scanning, Muffle Furnace, short pinning for post processing. And we have exclusively softwares for mimics, as we discussed, like for medical image processing, and Magix is for preparing the STL files and some extent designing the products, and thematic again the customized implants design, and catalyst and 3D export for simulation of metal 3D printing process. So these are the softwares which are dedicated for 3D printing at our facility. So our group. So then, yeah, and we are also running an MTech course as well as a PG diploma course in additive manufacturing from NIT Warangal. So yeah, this is what from my side. So if you're having some questions, yes, I'm very happy to answer those questions. And do you have any um, discussions? It is over to you, sir. Uh, then we'll have the discussion. Yes.
Yeah, thank you very much, sir. Yeah, participants, over to you. If anything to be discussed, please discuss. If anyone working in the area of this medical field, they can discuss a very good topics are as covered.
Sir,
Yeah, Nimisha, go ahead.
uh, I want to ask a question to sir that somewhere in this process means when we are manufacturing the 3D printed implant, before implanting it into the human body, will you go for some kind of analysis that which will facilitate, which will be for like checking which material will be appropriate, which material will be having that particular properties
Yeah.
that can be biocompatible or it can be mechanical properties. You go for this kind of analysis before implanting.
Yeah, definitely. Yeah, why? Because some extent, like we are taking, say for example, titanium 64, that is medical grade, which has been approved by FDA. And as you said rightly, like whether it is um, say sufficient strength for making use of replacement of the joint or replacement of a particular bone. Yeah, definitely. We Yeah, that's what we have done a FEA analysis for doing or getting the idea like what sort of whether there are some failures or whether it could be standing or not. Yeah, definitely, and even some extent in vivo in vitro tests also. It has been already proven. That's what like where titanium 64 is the one grade which we have considered. But though it has some sort of limitations as far as the other properties are concerned, but it is quite say suitable for other characteristics that we are looking at. So definitely we need to analyze before it is getting implanted, and some constraints also there, like say you may be looking at some other material, but it's a quite challenge like whether it has been say compatible with 3D printing technology. That also we need to consider. But majority of the times, the titanium alloy 64 is proven in the literature as well as the certification authorities. And as you said, like the firmware and the sort of mechanical properties or the loads that has been. But here, um, we are not into an orthopedic related application, but oral maxillofacial, you need not find much of the loads, maximum chewing force or the biting force. So it may not be much if you compare with other orthopedic areas. So definitely, before it is getting fixed, we need to check it for the failure